Welcome to the Picture Language Seminar. It's a beautiful day here in Cambridge, though very cold, but we have quite a warm reception for our speaker. And upcoming, we have talk by Kai-Feng Bu, Matthias Christendal, Stefan Voss. We have a very mixed set of speakers from the quantum information side, from the physics side, and from the side of mathematics. And we're ending up the ones I've listed here with 2 experimental physics talks, which will be extremely interesting. Today, we're very happy to have Christopher Ryba. He had been a graduate student at MIT with Pavel Ettinghoff, got his degree recently, and is now at the University of California, Berkeley. Will tell us about stable character polynomials for symmetric groups. Christopher.
Thank you very much. Thanks for the introduction, and thanks for the invitation to speak. So I should confirm before I start that people can see my screen. Is that correct?
That's right.
All right, excellent. So I gave some thought as to what's the best way to give this talk, and I decided that it would be more cohesive to phrase things in the language of general linear groups rather than unitary groups, but the representations of those 2 groups are essentially identical. So if you feel that in any way it feels unfamiliar, all I want you to do is think about unitary groups. All right. So a object that is going to play a prominent role today is that of partitions. So just to make sure we're on the same page, a partition is going to be a sequence of positive integers, here lambda1 through lambda r, and I'm going to insist that they're sorted from largest to smallest. And when I consider a vector of them, which I denote here by lambda, that's going to be a partition. And there are 2 quantities associated to partitions that are important for us. The first is the size, which is just the sum of all of the parts. And the other is the length, which is the number of them. So it's common to depict these diagrammatically. In this case, I'm going to use what's called English notation, where I'm going to have a collection of boxes. And I'm going to have one box for each part of a part. I guess in each row, I'm going to have a number of boxes equal to the first integer in the first row, the second integer in the second row. So here we have 3 in the first row, so we have 3 boxes in the first row, and 1 is the second entry, so we have 1 box. And now I want to do a modification of this concept a little bit, and I want to introduce this notation lambda square brackets n. And all this does is pad my partition in the first entry with however many boxes are necessary to make the total size n. So in this case, what I've done is I've taken n minus the number of boxes in the remainder and put those in the first row. So in this particular example, I have the partition from above, and I've completed it to have a total of 10 boxes by sticking 6 on top. And so it turns out that if n is not big enough, if n is relatively small, then this first row might actually be shorter than the next row. And so it wouldn't satisfy the definition of a partition because it violates this inequality. So we have to be a little bit careful about that. But in most cases, we'll just consider n to be large enough so that is fine. If n is small, then we can still make sense of that situation, but it's a bit more intricate and I don't want to get into the details right now. And with that, let's move on to representations of the general linear groups. So I have for you this quote, which I quite like, by Graham Higman. The representation theory of the general linear groups must be rewritten by each generation in the idiom of the day. And I don't know if this was intended as a command or was a prediction, but certainly it has come to pass. So here are a few examples. And so the first and perhaps my favorite is Schur duality. So one takes the vector representation of the general linear group and considers the d tensor power of it and finds that you have an action of the symmetric group by permutation of tensor factors that commutes with the action of the general linear group. And with a sufficiently detailed understanding of these two group actions, you can relate the representation theory of the general linear group with that of the symmetric group. I want to point out at this moment that actually the roles of the general linear group and symmetric group are not quite interchangeable here, because this space that we're acting on is a tensor power of a representation for the general linear group, but it is not a tensor power of a representation for the symmetric group. Another approach is highest weight theory for Lie algebras. So you can pass to the Lie algebra and you can take a triangular decomposition and go from there. That's also a fairly classical construction. A construction that we'll say a bit more about in a moment is a geometric approach, which is the Borel-Weisbot theorem. And that works by considering the flag manifold of the general linear group, on which one can construct certain equivariant line bundles. And then the cohomology of those line bundles inherits an action of the group. And it turns out that that is one way, by considering this cohomology of line bundles, to obtain the irreducible representations. Another approach is more combinatorial in nature. It's the theory of crystals. It's related also to crystal bases and quantum groups. I won't say anything about that. And another one that I wanted to mention, just to make the point that there's a wide variety of options, is the geometric Satake correspondence. And this seems to be really quite sophisticated in terms of using things like perverse sheaves on affine Grassmannians and things like that that I won't talk about at all in the remainder. All right, so as you can see, there's a lot of different approaches to representations of general linear groups, and they have their emphases and advantages and disadvantages. So depending on what you're doing, you may want to think about it in a different way. But I'll want to actually explain what they look like. So let's review what a representation actually looks like. So I'm going to use this slightly strange notation for irreducible representations. I'm using the notation of Schur Functions, but what this means is the irreducible representations of GLN associated to the partition lambda. The reason I'm writing it this way is because when I write something applied to C to the n, it's relatively clear that it's the general linear group GLN acting on this and not a different general linear group. Later on, I'm going to want to consider the action of two general linear groups simultaneously. And so this distinction is helpful. But in any case, the permitted representations are indexed by partitions that can have any number of boxes, but at most n rows. So some people may notice that this is not strictly correct, that I'm talking about polynomial representations rather than algebraic representations, but the difference is very minor. So we don't really lose anything by considering just things indexed by partitions.
Sorry, but what is your ground ring or round field for GLN, right? Because for GLN, right, you can take many fields or rings, and it's really such a variety that how you treat it all in the same time.
That's fair. So for the purpose of this talk, everything is going to be over the complex numbers. Probably you'll be able to relax things to field of characteristic 0, but let's stick with the complex numbers to make everything concrete. So I want to define a weight vector. So a vector is going to be a weight vector of a given weight, which is going to be a sequence of, again, integers, if it satisfies the following equation. So here what I have is a diagonal matrix whose diagonal entries are x1 through xn, and I apply it to V. So when I say apply, I want to emphasize that this matrix should be viewed as an element, an abstract element of this group, acting on a representation of the group. So it may not necessarily be acting by multiplication of a matrix on a vector, as you would think maybe when you write a matrix times a vector. So actually the matrix representing the action of this group might be something different. And in fact, it's sort of implied by this equation that it's going to be, or at least have one entry if you pick a basis including V, that is this expression in terms of the diagonal entries. So what I've done is I've just taken the diagonal entries, raised them to the powers of this weight, and said that is the scalar by which this group element must act on this vector. So what one can do is one can in fact find a so-called weight basis of this irreducible representation, which is to say a basis consisting of weight vectors. And then the Schur function, which is one of the protagonists of this talk, is simply going to be defined in terms of taking the trace of a diagonal matrix acting on this irreducible representation. So if I have a weight basis, then the action is in fact going to be diagonal. And so all I need to do is to compute the trace of the action, I need to add up the diagonal entries. And so the entries are going to be these monomials in the xi. And the number of times I get this monomial is equal to the number of basis vectors with that particular weight. And that is the dimension of the so-called weight space of this representation. So in the case where the partition lambda is just 1, that is to say has one part of size 1, then the irreducible representation is just the vector representation. In that case, the representing matrix is this same matrix. And correspondingly, its trace is the sum of the diagonal entries, namely the xi. So there's one more detail that I want to point out here, which is that in this expression for the Schur function, there's implicitly an n on the right-hand side, which is telling you which general linear group is acting. And then there is no n in this notation on the left-hand side to tell you which general linear group I started off with. The issue here is that I'm using the same partition to index representations for different groups. So a priori, it's not clear which group this is supposed to be a character for, or which group it is a trace of an element of. But it turns out that actually that there's a sort of universal object, which is going to be a symmetric function rather than a symmetric polynomial, which means it roughly that it has an infinite number of terms. So in this case, you can imagine writing down a formal expression, which is a sum of infinitely many variables. And then to recover the Schur function for the particular general linear group, what you do is you set the appropriate number of xi to be 0 until you have n of them left, and then it will be a character for GLN. Perhaps I should make one other comment, which is you might think that we lose a lot of information by restricting ourselves to diagonal matrices. But if you remember that the trace is conjugation invariant, then what you can do is you can take any diagonalizable matrix and you could conjugate it to be in this form. And then you'll be able to express the trace in this way, where the xi are going to be the eigenvalues of the matrix. And then diagonalizable matrices are a much larger chunk of the general linear group than just diagonal ones. So actually, this does remember quite a lot of information about the representation. Last comment about this, which is you can, in fact, conjugate this diagonal matrix by a permutation matrix, which has the effect of reordering the elements on the diagonal. And that means that actually the expression, being conjugation invariant, must also be invariant under swapping the xi's. So actually this S lambda is guaranteed to be symmetric. So similarly, in this expression, which is the sum of the xi, doesn't matter which order you write them down, the sum will always be the same. All right, so we've defined what a Schur function is. One of the key properties that I want to emphasize here is that if I have, let's say, two vectors with particular weights, and I consider their tensor product, then the weight of the tensor product is itself going to be a weight vector, and its weight will be the sum of the two weights. So these two weights are actually vectors of integers, and when I add them, I really just mean the component-wise addition. And the monomials that we attach to them, you'll notice, obey exactly the same rule under multiplication. So if I take these monomials that appeared in the expression of the Schur function and I multiply them, the exponents are just the sums of the entries of mu and nu, which is precisely a corresponding entry of the sum of the two weights. And the upshot of that is that if I consider the tensor product of two of these irreducible representations, and I ask, how does that decompose in terms of irreducible representations? These structure constants or fusion rules simply become something that can be computed in terms of polynomials. So these structure constants, which I can compute using just a bit of algebra, I write down what the Schur function is, and I multiply them, and I express it in terms of more Schur functions, something that's pretty accessible algebraically. So these Littlewood-Richardson coefficients are pretty well understood. There are various rules for computing them, and I'll make one more comment, which is that because the Schur function is homogeneous, that means that when I multiply two of these things, the degrees as polynomials add, and that means that this Littlewood-Richardson coefficient will be 0 unless the size of the partition lambda is equal to the sum of the sizes of the partitions rho and sigma. And so here's an example. So recall that S1 is going to be the character of the vector representation of GLN. So when I consider the product of it with itself, secretly I'm considering Cn tensor Cn. And when I expand this out, I can decompose it in this particular way. The reason to do so is that these respective factors are the Schur functions associated to the partitions 1, 1, and 2 respectively. So you'll recognize this as the character of the exterior square and the symmetric square, if you are familiar with this theory. So this is I guess, a algebraic manifestation of the fact that a tensor square decomposes as a symmetric and alternating square. Okay, so now that we know what these things look like, let me tell you about the Borel-Weber theorem. So first of all, I need to introduce a geometric space, which is the flag manifold. And what I'm going to do is I'm going to consider nested subspaces of C to the n. So I'm going to have n of them, or perhaps n plus 1, depending on how you choose to count. And each one will have dimension 1 larger than the next. So I start off with the 0 subspace, and I ask for that to be contained inside a subspace of dimension 1, and ask for that to be contained inside a subspace of dimension 2, and so forth. So such a configuration of subspaces is called a flag, and the set of all of such flags is the flag manifold. It turns out to be compact, and it also has an action of the general linear group. And that simply acts by essentially matrix multiplication on each subspace individually. So if I have, let's say, an R-dimensional subspace of C to the n, and I apply my favorite matrix inside GLN to it, it'll take it to a different, possibly R-dimensional subspace. And if I had a subspace of that, it would be taken to a subspace of the new one. So it preserves this relation of subset but not equal to, and therefore gives me another flag. And so it turns out that there's some recipe, given a weight mu, of producing a line bundle on this space. And so the Borel-Weber theorem is about the cohomology of these line bundles. So it turns out that they are 0 in all degrees except possibly 1. And if it is non-zero in some degree, it turns out to be irreducible. And in the case where the weight that I put in is a partition, which is to say that the parts are ordered, then the cohomology is simply the irreducible corresponding to the same label. And of course, that forces all the remaining cohomology groups to be 0. On the other hand, if mu is not a partition, then it's a bit more complicated to say what happens, but there is a definite algorithm that one follows. So roughly speaking, there are certain rules that allow you to essentially try to order your weights to give you a partition. And if you are able to do that, then you get the irreducible corresponding to the partition you obtain by doing so. And the cohomological degree that it lives in is equal to the number of steps that the algorithm took. However, it's also possible that the algorithm won't let you produce a partition at the end. And if you can't do that, then the cohomology is 0 in all degrees. So this is a more geometric approach to the representation theory of general linear groups. And now I want to tell you about symmetric groups. So similarly to before, there's a wide variety of ways you could approach this topic. Perhaps the most classical is that of Young symmetrizers, where one takes carefully defined symmetrizing idempotents and anti-symmetrizing idempotents and combines them to define the irreducible representations. A more recent approach is that of Okunkov and Vershik, which works by understanding the branching rules when one restricts from success from one symmetric group to a smaller one. And it has had a lot of applications, so it's very popular. Another one is the so-called duality with partition algebras, which is related to things like the Lie categories. So similarly to what we saw with Schur duality, one considers the permutation representation of the symmetric group. So one takes C to the n, where the symmetric group acts by permutation matrices, essentially permuting the coordinates, and takes a deep tensor power of that. While this retains an action of the symmetric group on the elements by permutation of tensor factors, in fact, a larger thing acts, and that is the partition algebra. And so again, by understanding this action with enough detail, one can relate the representation theory of the two objects, and as a result, obtain some understanding of the representations of the symmetric groups. And the last one that I mentioned, just for flavor, is you can also realize irreducible representations by a homology of Springer fibers, which is perhaps a more geometric approach, but I won't be saying anything more about that. So one comparison that I want to make is that some of these things are very analogous to what we saw for general linear groups. For example, this duality, as I alluded to, is similar in very many ways to Schur duality, whereas some of these constructions are only loosely analogous to the general linear case, and some have no clear analogy at all. So I should mention, for example, that there's no theory of crystals on this list, crystals for the symmetric group. And it would be a very exciting development if someone could come up with a theory of crystals for the symmetric group. So I want to mention something about the actual representations of symmetric groups, as I did for general linear groups. So I'm going to describe them or index them by partitions of size n, where n is going to be the parameter of my symmetric group. So these Specht modules, which I'm going to denote with a script s, are parameterized by partitions of a particular size with no restrictions on the number of parts. And so according to the standard convention, if I consider the partition that has just one part, n, so diagrammatically, it would just be a row with one row with n boxes, that corresponds to the trivial representation. Whereas if every row has one box, so it's secretly a column, then that's the sign representation. And again, one can consider tensor products to get the fusion rules. And so these are given by so-called Kronecker coefficients. So these fusion rules, which I denote k mu mu lambda, are much more poorly understood than the Littlewood-Richardson coefficients. In fact, it's a very famous problem to give a combinatorial interpretation of these. People would be looking for something similar to what is known for Littlewood-Richardson coefficients. But actually, there's quite a large difference between them. It's a celebrated result that, for example, you can compute Littlewood-Richardson coefficients in polynomial time. On the other hand, it's been proved that computing Kronecker coefficients is NP hard. So it suggests that a description of these things has to be somewhat complicated. So unlike the case of general linear representations of the general linear group, there's no maximal torus inside the symmetric group. It's a finite group. It's a different kind of beast. And so we can't really think about weight spaces and write down a character in such a straightforward way. And so the main purpose of this talk is to try to remedy that. So for that, I want to actually do a bit of a subtle change of the setup. And what I'm going to do is I'm going to consider a family of representations for varying symmetric groups. So I'm going to fix a partition lambda, and I'm going to consider lambda square brackets n for a variety of n. And as n gets larger, then I'll get representations of larger and larger symmetric groups. So they're not a priori directly related. But what one can do is one can consider the Kronecker coefficients for these triples. I fix my favorite partitions, mu, mu, and lambda, which can have any sizes, because as soon as I take square brackets of n, that completes it to a partition of n, and then I'm allowed to take the tensor product and ask for the fusion rules. it turns out that if I do so, and I consider n getting larger and larger, this sequence of fusion rules eventually stabilizes. So this eventually becomes constant, and the resulting quantity, which I denote with a k tilde, is called a reduced Kronecker coefficient. And so somehow this is a stability phenomenon, which is a popular term in certain parts of representation theory. So for this reason, and also some other reasons that I haven't described, you might be inclined to think that the complexity, in some sense, of this irreducible representation or Specht module is controlled by lambda rather than the whole partition. So in particular, the top row doesn't tell you much about the complexity in any sense. And so one sanity check of this idea is that if you consider the trivial representation, then that corresponds to just a row. So if you were to express it in this format where it's lambda square brackets n, you'd have to take lambda to be the empty partition because there are no boxes below the top row. So in that case, the size of the empty partition is 0. And the trivial representation is the one of minimal complexity, which hopefully agrees with your intuition. So now I want to take the talk in a slightly different direction, and we'll link up with that a bit later. This is also the part where I introduce a second vector space into the equation. So here, V is going to be a vector space, and it's going to be different from C to the n. So given a vector space V, I want to consider the free Lie algebra on V. And for example, or I should say what it is simply the set of Lie brackets in vectors in V that satisfies, or that are only required to satisfy the minimal properties to define a Lie algebra, namely linearity in each of the factors of the Lie brackets. It needs to be skew symmetric. So if you swap the two arguments of a Lie bracket, you incur a sign, and it needs to satisfy the Jacobi identity. And so as soon as V is two-dimensional, suppose I have linearly independent vectors V1 and V2, then I can form iterated brackets such as V1 bracket V2 bracket V2 bracket V2. And these in general will be linearly independent. And so this means that this free Lie algebra is a big infinite dimensional thing. But it turns out to be exactly the right thing to consider for what I'm about to tell you. Let me consider n copies of the free Lie algebra, which I'm going to write as a tensor product in this way. And the reason that I write it in two different ways is that when I consider n copies this way, it's clear that it's still a Lie algebra, just because each component is a Lie algebra. And when I write it this way, it's clear that it has an action of GLNC, although just on this tensor factor here, although that action does not necessarily respect the Lie brackets. If you think about which things do respect the Lie brackets, it turns out that it is the permutation matrices which do, because they just reorder the factors in this expression or decomposition of Lie algebras. So we have automorphisms of the vector space V acting on the free Lie algebra on V. And we also have the symmetric group acting on this thing by Lie algebra automorphisms, where this symmetric group action is restricted from the general linear group. And so what I can do with that is I can consider the Lie algebra homology of this new Lie algebra with coefficients in a particular module. So this module is a symmetric algebra on the vector space V, and the action of the symmetric group on it is taken to be trivial. So I'm not going to say too much about what the module structure is. Just take my word for it that there's only one sensible thing you could do. And the upshot is that this quantity is going to be a representation of this group, because these are automorphisms of this Lie algebra, and this is an equivariant module for it. One way of computing these homology groups is with the Chevalley-Eilenberg complex. And in that case, the terms of this Lie algebra homology are, of the complex, are given by exterior powers of the Lie algebra tensored with the module. And I want to emphasize that this expression, where I take an exterior power of this quantity, is going to be a representation of GLN just because that was the case for the underlying Lie algebra. And so this complex can actually be taken to decompose, or to break it up. And what I want to do is I want to consider just the components that transform in a particular way according to this group, GLV. So I'm not going to tell you what the differential is in this complex because I'm never going to use it. But it turns out to be equivariant, or to respect the action of this group. So what I can do is I can say, give me the subcomplex that is essentially the isotypic component of some irreducible of GLV. And what's left, when I do that, will still be a complex. And here, this prime on the partition lambda is the transpose. It just reflects it in a diagonal. The rows becomes columns and the columns become rows, but that detail is not particularly important. What I really care about is what's left over when I do this operation. And that's going to be denoted by script L. So what I've done is I've said, I want to, for some particular reason, consider this Lie algebra homology, and I have a particular method of computing it. And when I consider that computation, I'm led to consider these particular complexes. So I give this the name Littlewood complex in analogy to other things that have been called Littlewood complexes in the literature. And each of these individual terms is a representation of GLNC. And so because it's a representation of GLNC, you may associate to it a character, which is going to be a sum of Schur functions. So I'll mention or emphasize that the differentials do not respect the action of the full general linear group, only the symmetric group. So let's do a quick example. What I'm going to do is I'm going to take this partition with just one box. In that case, the complex becomes the following thing. So the first term is the vector representation. And then the second term is the trivial representation. So these are both representations of the general linear group, but this map is going to be only a map of representations of symmetric groups, because the full general linear group was not didn't define Lie algebra automorphisms, and so it didn't necessarily act on the Lie algebra homology. So what is this map precisely? If I write out c to the n in terms of coordinates, say the coefficients or coordinates of z1 through zn, then the image under this map is just going to go to the sum of coordinates. And so you can see that if I were to permute this vector, then I would not change the sum. And correspondingly, the action on this factor is trivial. So this confirms what I asserted, that this should be should respect the action of the symmetric group. And now let's see what the homology is. So in perhaps the degenerate case, when n equals 0 and there's actually nothing here, then the homology is forced to be the trivial representation on the right. If on the other hand, n is equal to 1, which could also be viewed as a degenerate case, then actually this map becomes the identity between C and C. And in that case, the homology vanishes. And then the final case is everything else. When n is at least 2, then this map will be surjective, but there will be some kernel on the left. And that kernel is going to be vectors of mean 0, which again, you can observe are going to be a sub-representation for the symmetric group. Because if a sum of the coefficients is 0, then reordering those coefficients will still give me something with sum 0. And in fact, it turns out to be irreducible. It turns out to be precisely the Specht module indexed by this partition, which you might also write down as 1 square brackets n, because it has 1 below the diagonal, and then it's completed to be a partition of size n by adding a first row of the right size. And I want to point out that n greater than or equal to 2 is precisely the condition we would need for that square bracket realization to make sense. Otherwise, it would be too small. It wouldn't define a partition. So the theorem that I want to mention is precisely about the homology of this complex. So if n is large enough such that lambda of n is a partition, then actually this behavior is general. Then this complex which I defined gives me the Specht module associated to lambda square brackets n in degree 0. I guess 0 here I'm taken to be the far left of the complex, and in degree lambda. So lambda is on the far left and 0 is everywhere else, or all other homology groups vanish. On the other hand, if lambda is small, then this is no longer the case. But we still can tell you exactly what the homology of this complex is, and it's given by exactly the same rule as the one in the Borel-Weber theorem. Actually, this situation is slightly simpler because there are fewer things that can happen in this case. So we don't need to use every possible situation that arises in the Bott theorem and the Borel-Weber theorem. So this is roughly like Borel-Weber for symmetric groups. The similarities are striking, but there are also several uncomfortable differences, which is that Borel-Weber is widely thought of as a geometric theorem that one thinks about spaces and line bundles. But if one tries to mirror exactly the setup for Borel-Weber and reconcile it with what we've done here, you're led to consider things like projective varieties whose homogeneous coordinate rings are some non-commutative algebra. And that doesn't seem to make any sense. What should a variety with a non-commutative coordinate ring be? Well, I don't have a particularly satisfactory answer to that. And similarly, the space that it's actually describing is supposed to be some sort of Grassmannian for the symmetric group. And the symmetric group being a finite group, it's totally unclear what that should be. So let me say a bit more. So I can take the Euler characteristic of this complex, and so this will tell me something about the homology. And I said that each of the individual groups of this complex are necessarily representations of GLN. So I can take their characters, and they're going to be some Schur functions or sum of Schur functions. And so what I get is some alternating sum of polynomials. And this appears already in the literature as the irreducible character basis of Oriana and Zabrodsky, and also by the name stable Specht polynomial in the work of Asaf and Speyer. So while this is a known quantity, it does have some interesting properties. So first of all, let me comment on how it behaves when you try to interpret as the trace of something. So the representations of GLN, which were going into this, were not a priori related as representations of GLN. They only had a differential relating them as representations of symmetric group. So I should only try to evaluate them at eigenvalues of permutation matrices. But if I do that, then what I get is the character of the associated permutation acting on a particular Specht module. And it's not too difficult to deduce from that actually these polynomials multiply with structure constants that are the fusion rules for this sort of stable setting, the reduced Kronecker coefficients. So there are a few other facts for this that I want to mention. The first is that it turns out that this stable Specht polynomial, or I guess I refer to it as a stable character, is to leading order the same thing as just the Schur function. But unlike the Schur function, it's not homogeneous. It has lower order terms because the complex is not concentrated in a single degree. One conceptually nice property of it is that there's this truncation procedure to recover the honest Kronecker coefficients from the reduced ones. So there's a way to pass back from the stable setting to the sort of finite one, which perhaps you might care more about depending on your point of view. And this complex, which I constructed for you, actually has some more motivation for its own construction, which is that Sam and Snowden define particular categories. They write rep S infinity. And it's not the full representation category. It's not all representations of the infinite symmetric group, because that would be too large, but it's a carefully selected subcategory of those. And it turns out that inside there, this complex will give us injective resolutions of simple objects. And I guess I should explain a little bit more about that. I should just say that I've been pretty cavalier about what n actually is. I've been saying, oh, it is a positive integer, usually large enough that we don't have to worry about certain things. But in fact, you can take n to be infinity. And if n is infinity, then you have a perfectly good action of symmetric group S infinity. And then everything turns out to live inside this category. And what's very remarkable about this category is that if you understand this S infinity case sufficiently well, then you can actually specialize. You can sort of set infinity to be whatever you want, which is a bit of a counterintuitive thing to do, but it turns out to be possible. And one more comment I'll make is that I can take my ordinary Schur function and I can consider its evaluations at the eigenvalues of permutation matrices. And that should give me the character of some symmetric group representation, precisely the character of the restriction of the irreducible associated to lambda from GLN to Sn. And so if you think about the things that I've told you, it turns out that the restriction multiplicities are precisely the constants which control how the Schur functions decompose into these. And part of the reason that I mention this is that it's also an unsolved problem to give a combinatorial interpretation for the constants that come out of this restriction. In particular, what I've told you implies that there's some sort of stability as n goes to infinity. Okay, so let's revisit our example. In this example, we had this complex before, and so we had the vector representation, whose character I said was just the sum of xi's, and then the character of the trivial representation is just 1. So when I take the Euler characteristic, I take the alternating sum, and so I just end up with a sum of xi minus 1. So what happens when I take this thing, which I want to think of as the character of, in some sense, of the mean zero vector representation of the symmetric group, and I multiply it by itself? Well, you can do some algebra and you can expand it out, and the resulting thing you can parenthesize in the following way to give 4 terms. And the reason I've done it in this particular way is because those 4 terms happen to be these stable characters. So I want to emphasize that here you see the Schur function associated to the partition 1, 1. And here you see the Schur function associated to the partition 2. And that's not a coincidence. One of the facts I mentioned on the previous slide was that these stable characters are to leading order just Schur functions. And so that means that the leading order multiplication will be the same as for Schur functions. And so that means that the reduced Kronecker coefficients that are coming out will in fact be the same things as the Littlewood-Richardson coefficients associated to those partitions. So you might remember that when we did this calculation for Schur functions, so without all the daggers, then we just got these first 2 terms. And so here we had a partition of size 1, here we had a partition of size 1, and we got partitions of size 2 out. And then there are some lower order terms, which are not controlled by that. But as far as this leading term is concerned, it's the same as for Schur functions. One property that I should mention is that actually these stable character polynomials are somewhat more complicated than Schur functions. So the leading order term is completely under control. But then to define the lower order terms, or to sort of give a formula for them, involves an operation called plethism. And plethism is the bane of combinatorialists. It's the sort of operation that they would very much like to have a combinatorial interpretation for, but it seems to be completely elusive, even in some very basic examples. So to write down these things in general, it's very far from trivial. And so I want to say a few things that you can do with this, and also a few things that remain to be done. So when Asaf and Speyer wrote down these expressions, they considered them sort of purely combinatorially. They didn't think about any complexes, but rather about symmetric functions. And they noted that in their calculations, the character of the free Lie algebra was appearing, but they didn't have an explanation for it. And this approach does give an explanation because we considered the Lie algebra cohomology of something very close to the Lie algebra. And also there was a conjecture about something called symmetric sieving, which is a variant of something called cyclic sieving. So again, combinatorialists sought to understand certain actions of the cyclic group on some important sets. And they found that there's a lot of data about the action contained in particular polynomials. You can associate a particular polynomial to a particular group action, and if some circumstances hold, then it's said to exhibit the cyclic sieving phenomenon. And so you can think about upgrading this from an action of the cyclic group to an action of the symmetric group. And a slight modification of the argument that I've given here, which is actually a bit easier than what I've discussed, proves a conjecture of theirs for a particular formula on a particular construction. And some other things that remain to be done are essentially, is there really some geometry behind this? So as I alluded to when I made a comparison to the Borel-Weber theorem, the issue that I had was I had to understand varieties with non-commutative coordinate rings, and it was very unclear what that should be. And so it would be nice to be able to put it on the same footing and say, this is how you should think about it. But that seems to be totally out of reach. Another property that would be very desirable is to have a combinatorial expression for these stable character polynomials, of which there are many for Schur functions. So a Schur function can be expressed as a sum over a semi-standard Young tableau. And it's unclear if you can do anything similar for these polynomials here. And because these things are so difficult to write down, you might think that the answer can't be straightforward, but we really don't know. And perhaps the last thing that I'll mention is that there are several constructions which are similar to this one, but they all focus not on the symmetric group, but on classical groups, such as the orthogonal or symplectic group. So they are in particular Lie subgroups of GLN. And so the construction or the similarity is that it is a resolution of irreducible representations by things that are restricted from this general linear group, which is larger. And this theory was worked out by Sam and Snowden and Weyman. And one of the features there is that it can be written in terms of ordinary geometry, or algebraic geometry. So it does involve commutative things. And our construction is different from all of these in its non-commutativity. But even they, in the classical group setting, didn't find an entirely satisfactory uniform construction across all cases. They had to sort of go case by case for a few of them. And so it would be very nice to be able to provide something that hits all of those things at once, especially the non-commutative case. Okay, I think I'll stop there and I'll invite questions. Thanks for your attention.
Well, thank you very much, Christoph, for a very interesting talk, Christopher. And it's very stimulating, so I hope there is a great deal of discussion.
Hi, Christopher. Thank you for the beautiful talk. I have a question. This is a very beautiful geometric interpretation of the fusion rule coming of those Schur functions. And in our joint paper, we also have a fusion rule for the skew Schur functions. And that has somehow, that should be related to a symmetric space, a pair of Lie groups, inspired by the connection in conformal field theory. So could you run your method to give a geometric interpretation for our fusion rule?
I'm not quite sure what to say. I must confess that I usually don't like to think of these things particularly geometrically. So I may not be the best person to ask. I don't know if I can really say anything wise here.
But do you any work in this direction, like considering the geometric representations for conformal pair instead of one or maybe one family of the groups?
Well, I'm not thinking about it at the moment, but definitely there has been some work in that direction. I am not sure if Sam and Snowden have related results, but they very well might.
Thank you.
So Christopher, do you have a reference for your recent theorem?
So I have a paper on the archive, which goes perhaps into a bit more detail. Maybe I can just quickly confirm what its name is, because I apparently don't remember these things. It is Littlewood complexes for symmetric groups.
Can you type it on the chat box?
So are you saying, Christopher, you have a new type of duality here that you've discovered? That
well, I feel like that might be an overstatement. Yeah, I wouldn't go that far, but it's definitely something that I don't feel that I understand to my satisfaction. And I want to know how it fits better into the landscape of representations of symmetric groups. For a while, I've wanted to be able to have a geometric interpretation of the representations of symmetric groups that's satisfactory to me. And while this accomplishes some of those goals, I don't understand it as well as I would want.
Sorry, can I maybe say orthogonal question? Hello?
Hello?
This concept
sorry, if I recall correctly, the poles are relative around the terms, but that's probably most closely the case for groups. And that brings in the connection to measured in integrals over unitary groups, or it brings in the use of your flag manifolds. Any decomposition that I can take advantage of there that you're with regard to the flag manifolds and these symmetric groups? There's an intriguing connection there that I'm not quite sure I've latched onto.
Well, I'm
not sure
I don't think that I think I understood enough of your question to give a bit of an answer, but please let me know if it doesn't address your question. So At the moment, I'm very hesitant to say anything about.
It's a vague question. It's just
right. So I would very much like to know what a flag manifold for the symmetric group should be, and unless I first know what that is, it's difficult to speak of analytical properties of these characters. So one of the naive definitions you might try to give is as a sort of flag of subsets of the numbers 1 up to n, which is a natural thing that the symmetric group acts on. But if you do this, you wind up with something pretty trivial, and certainly something that doesn't recreate the sort of richness of the representations of symmetric groups. So I really don't know what a flag manifold for the symmetric group should really be. So it's a great question, but I don't have an answer.
okay. Thank you.
So Shengwei, is this related to your Schur duality for quantum groups?
Well, certainly we both use Schur duality, and we use those Schur polynomials. And actually, in joint work with Christoph Ryba, he has this key idea to compute the fusion rule using the symmetric polynomials, and we do use this very important result. This called well, Chris mentioned that name. I forgot that. Platism?
Platism, yes.
That's a very important method used in the proof. And I believe this method works in much more general case, and there are actually other evidence. The family we considered is the first family related to the symmetric space, the orthogonal group over unitary group, or symplectic group over unitary group. But there are other families, and certainly there are other families, and there are indications the method works. And also, since that's a symmetric space, and there's a part I do not understand very well, the connection between the symmetric space and the conformal pair, or this conformal inclusion in carry CFT. But there should be a very good geometric interpretation of this fusion rule using the symmetric space, and certainly not the finite dimensional one, since we also consider the generic case as a limit. So it's pretty similar to this Bott theorem, like this situation. And there's another subtle point to make a cutoff, like WGW cutoff, as we go from the continuum case to certain case as root of unity. And then it becomes discrete. And actually that part is very interesting, since for our case, it works, but it's highly non-trivial. So I'm thinking about the work of Christoph on symmetric group. Maybe it's reasonable to consider the continuous case as what he did now, and then consider a reasonable cutoff. And then that gives you the structure of symmetric group. But since I haven't done any computation on that, I'm not sure about it, whether this idea works. But this is a good idea for the Lie group and conformal pair case.
Did either of you talk to Borden? Because he's done so much work on symmetric groups of arbitrary dimension.
I haven't spoken to him, but I'm familiar with his work to some extent. And in a way, this is much more restricted than the sort of things that one's led to consider in his work. So he talks about representations of infinite symmetric groups, but there's a wide, if you like, a zoo of such things. So there's some sort of cone parametrizing the irreducible representations, most of which are infinite dimensional, or almost all of which are infinite dimensional. And everything I spoke about today lives on one extremal ray of that cone. So he lives in a much richer world in that respect.
Right, we should have tried to get him to come to your talk. Are there any other comments or questions? Well, if not, I want to thank you again, Christopher, for a wonderful talk. It will be available on YouTube, and the slides are on your website and also on the Picture Language website. So thank you again, and see you next week.
Thank you very much.
Bye-bye.